In the previous video, I walked through building an AWS VPC network manually, with a public subnet behind the Internet Gateway and a private subnet routing through a regional NAT gateway. The network works perfectly, but there's one problem: cost. A NAT gateway continues to incur charges even when it's idle. In this video, I will show you how to take that existing setup, specifically the regional NAT gateway, and bring it under Terraform management so it can be controlled programmatically. We'll cover importing the existing NAT gateway into Terraform state, aligning Terraform configuration with the actual AWS infrastructure, using Terraform to quickly destroy and recreate the NAT gateway to reduce costs. If you are looking to move from manual build infrastructure to something repeatable, controlled, and cost efficient, this is the next step. Let's get into it. First, we're gonna create a folder and initialize a workspace. We need to configure Terraform and tell it what provider to connect to. In our case, the provider is AWS, and we also want to tell it what network resource to manage. To save time and keep the video concise, I have put all these configurations in one file for download. The link is in the description below. The first line of the file specifies the provider, which is AWS. The rest of the file defines the network resource we want to manage. The first one is a VPC, which is the base for everything else. The second one is the NAT gateway, and the last one is the routing table that contains the default routes pointing to the NAT gateway for internet traffic. If you recall from the last video, this routing table is the one that's associated with the private subnet. I kept the initial Terraform configuration at the bare minimum to get started. Terraform knows the file is for its configuration as the file name ends with .tf. When we run Terraform init command, it will go out, download the AWS provider plugin, and get the workspace ready for connection. Now it is the time to import configured network resources into Terraform. We are starting with VPC resource. In order to do that, we need to know the VPC ID, and that can be easily found out with the AWS CLI command as shown on the screen. The AWS CLI command outputs detailed information of two VPCs. One of them is the default VPC that comes with every AWS account when it is created. The other one, tagged with the name up247 VPC, is the one we are going to work on. We use Terraform import command followed by the Terraform address defined in the configuration file, and then the VPC ID. As you can see, the import is successful. So this looks great. We're going to do the same for the other network resources. We come back to the configuration file and get the Terraform address for the NAT gateway. And we also need the NAT gateway ID for the Terraform import command. Again, we're going to use the AWS CLI command to get the NAT gateway ID. Looks like I got a typo here. I'm going to correct it. Now we have the NAT gateway ID ready for import. Again, here we set the Terraform resource address followed by the NAT gateway ID. Import is successful. Next, we are going to import the route table containing the default routes to the NAT gateway. Same as before, we're going to use the AWS CLI command to get the route table ID. Sorry for the repeated typos here. Private subnet route table is what we want. Here we set the Terraform resource address for the route table, followed by the route table ID. Route table is imported. We can confirm the imported resources in state file by running the Terraform stateless command. As expected, 3 network resources has been imported. The TF state file contains detailed information of imported network resources. We can also use the Terraform show command to display detailed information for the imported network resources in local state file. Next thing we're going to do is to run the Terraform plan command to see if local state is in sync with the live AWS environment. We expect no changes to be made, but as you can see, there are 2 attributes to be updated for the NAT gateway. It happens because the AWS API recently added support for secondary IPs on NAT gateways. Since the code doesn't mention them, Terraform is just letting us know it's prepared to manage those fields if they ever change. This specific update isn't actually changing our live infrastructure. It's just Terraform filling in the blanks for new AWS features. Running apply now will update the local.tf state file to include those known after apply attributes. Once we do that, the next Terraform plan should come back with no changes. Now let's take a look at the local state of the NAT gateway of the apply command. As you can see, the 2 new attributes, secondary allocation IDs and secondary private IP addresses, has been added to the Terraform local state. Now let's run Terraform plan command again to see how it goes. No changes. This is exactly what we want. At this point, our Terraform local state has been synced up with the live infrastructure in AWS. Now let's manually make some changes in AWS by deleting the NAT gateway and see what Terraform can do about it. It takes some time for the NAT gateway to completely go away. Waited a few minutes. Now the NAT gateway has been deleted. Checking in the routing table associated with the private subnet, you can see the default route is now pointing to the black hole. Now let's see what Terraform got to say about the deletion of the NAT gateway. Terraform detects the change and tells us that the NAT gateway has been deleted. The plan also tells us the next apply will recreate the NAT gateway and update the routing table to remove the obsolete default route and add a new one pointing to the newly created NAT gateway. Let's actually do Terraform apply to see it in action. The apply will take a few minutes, so I'm just fast forwarding the video recording. The apply command completed with one resource added and another one changed. Let's head into AWS console to see how everything looks like. The NAT gateway has been recreated and available. The black hole in the routing entry can be cleared by refresh the browser. Everything looks fine here in AWS console. Now let's head back to Terraform to see the output of the Terraform plan. No changes, and that tells us Terraform state and AWS infrastructure are in sync again. With all resources under Terraform management, we can now test run deletion of the NAT gateway in Terraform. We can specify which network resource to destroy here. The command tells us the routing table will also be deleted along with the NAT gateway. Fast forwarding here to reduce wait time. NAT gateway confirmed deleted in AWS. Let's check the routing table. Refresh the browser page. We can see the routing table has been deleted as well. Let's see what the Terraform plan tells us now. It's planning to recreate the NAT gateway and the routing table. Let's apply the plan to complete the whole cycle. Again, I'm fast forwarding the recording to reduce wait time. The two resources have been recreated. Let's head to the AWS console to confirm. A new NAT gateway has been recreated and is in available state. Check the routing table and refresh the web page. We can see a new routing table has been added as well. The routing table contains default routes pointing to the newly created NAT gateway. So everything looks good here. And that's the full workflow. We started with the existing AWS VPC setup and brought the regional NAT gateway and the Terraform management. From there, we validated the entire life cycle, importing it into state, manually deleting it in AWS console, recreating it in Terraform, safely destroying it, and recreating it on demand. The key takeaway here is control. Once a resource is managed by Terraform, you are no longer tied to keeping it running all the time. You can treat it as something temporary, spin up when needed, tear it down when you don't, and directly reduce ongoing costs. And why this example focused on NAT gateway? The same workflow applies to other network resources as well. Whether it's the routing tables, subnets, or security components, the pattern is the same: import, align, and manage through code. If you find this useful, make sure to check out the previous video where I built this VPC manually, and consider applying this approach to your own AWS environment. Please help grow this new channel by hitting that like button and subscribing for more network engineering tips. If you have questions about specific resources you are trying to import, drop a comment below. Thanks for watching, and I'll see you in the next one.